All right. Welcome to today's community conversation. My name is Sean Hurley. I'm engagement manager and your host. We're joined by Dylan Smith and Craig Chester, and we're going to be talking about getting the most out of steep and shallow. So this is machining and Fusion 360. Community conversations are virtual meetups featuring expert speakers from across community. Sessions range from deep dives, tips and tricks, and live demonstrations on products such as AutoCAD, Revit, Dynamo, of course, Fusion 360, to roundtables on industry insights. All experience levels are invited to participate these. Let's go to the next one. This is the fun slide. This is going to be your favorite, Craig. Oh, sorry, that was my welcome. Let's go to the next, sorry. The safe harbor statement. This is one where the lawyers tell us that we need to let you know that if we make any forward-looking statements, talk about features that we're working on that may come in future releases, we like to be really transparent with you and let you know what we're working on and what we got going, but that you make any purchasing decisions based on the products as they are shipping today. So we can't make any promises, dates, that kind of stuff, but we will talk about things, that we may be working on for future releases or researching, and it's always nice to have those discussions. So next, please. Got some ground rules as we start today. Everybody's line is muted to reduce background noises. If you would like to ask a question, raise your hand using the Zoom function at the bottom, the little hand, or ask in the chat, and then when we get pauses, we'll take your questions to the speakers. This is a conversation, so feel free to ask something relevant to the discussion. You can have your video background on to kind of give a virtual in-person feel. It's not the same, but it's close. And we hope to be doing some community conversations at Autodesk University. So we'll have people in person as well as attending online. The recording will be posted to the event page where you registered, and also onto YouTube. So that's all I got to say about that. Everybody's being recorded. Introductions, the good stuff. My name is Sean Hurley. I'm Autodesk Community Engagement Manager. I'm a geeky technologist in Sunny Bend, Oregon. Over to you, Dylan.
Yep, so as you can see, my name is Dylan Smith. My job role is Customer Advocacy Manager for Manufacturing based in Birmingham in the United Kingdom. My job role entails working with customers, working with fabulous development teams, working with people like Craig. And in the past, I have been a CNC machinist, programmer, operator, all of that stuff. And now I get to use the software, help customers, and help better the product that we've got.
Okay, so hello everybody. My name's Craig Chester. I work in the product management team. I'm responsible for the milling side of Fusion and also for the PowerMill product. I've been working initially with Delcam, who were acquired by Autodesk, and then obviously Autodesk. So I've been in this similar kind of role for 35 years now. So nice to meet you all.
Okay, so I'll take over from here. So the agenda that we're looking at today, as hopefully all of you know, we are going to be looking at steep and shallow exclusively. We're going to be looking at how we can use it in 3 and 5 axis, and we're going to be around 35-40 minutes there. I'll keep an eye on my watch, and we'll get through as much as we can in that time. Craig's going to then take us through what's next for steep and shallow. It's going to be around 10-15 minutes-ish, and then we'll follow on with a Q&A, but of course, don't be scared to ask questions on the fly as we go along. So before we actually get into any product demonstration, and you'll be glad to hear that we are going to be spending most of this hour in Fusion 360, it's worth making everybody aware of what steep and shallow is. So it's a 3D finishing toolpath, which can of course be found in the manufacturing workspace, and you probably guessed, but it is designed to machine steep and shallow geometry. Now, when we think of steep geometry, think of things like vertical walls, but of course, not exclusive to vertical walls, and shallow horizontal floors, but again, of course, not exclusive to horizontal floors. It's actually a combination of various toolpaths. The steep regions are driven by the 3D contour toolpath, and the shallow regions are driven by 3D scallop and 3D parallel. As I said earlier, it can be driven in 3-axis, and it can also be fully 5-axis as well. And we are going to be going through all of that today, if time permits. It can be used for undercuts. We can use options such as optimized perpendicular passes, which probably won't mean much to you at the moment, but hopefully it will at the end. And we have the ability to avoid flat regions, which is all going to become apparent, and you'll realize why that's valuable in around 40 minutes. It also has the ability to evenly distribute points, which is very important. And again, we'll learn why that's important. So the bottom line, the overarching point here is that it's a very versatile and powerful toolpath strategy. And hopefully everyone will leave thinking that they must have it, they must use it, and it's really going to add benefit to their workflows moving forward. Okay. So you'll all be pleased to know that that's my portion of the PowerPoint all done, and we are going to look at the toolpath within the product now. Now, again, this is going to be very casual. It's going to be very conversational. So don't hesitate to put your hand up and unmute if anything isn't absolutely crystal clear. If I haven't described something and you don't understand it, just ask the question and we can absolutely answer that live. So first of all, we have a basic steep and shallow toolpath on the screen here. And firstly, it's worth noting that I have separated the shallow step downs different to the steep ones, so we can clearly differentiate between the two. And this standard steep and shallow toolpath shows exactly what it's all about. You can see here that we are machining the steep regions and we're machining the shallow regions. Now, the first point which many people have is, how do we differentiate between what's steep and what's shallow? So what we can do is go into the toolpath dialog form, and in the 4th tab, which is our passes tab, where we describe the cutting environment, such as step over, step down, tolerance, stop to leave, etc. Right at the top here, you'll see threshold angle under steep and shallow. Now, the threshold angle is the angle which differentiates the steep and the shallow. So the default distance, or the default angle, should I say, that we have here is 30 degrees. Now, if I exit out of this, what you're going to see at around 30 degrees here is that these passes that are offset from this point here start to turn into a different style of cut. Now, that's that 30-degree angle, and that's the default value, as I said. But if we wanted to, we could very easily go into here and we could change that. And everyone has preference. Sometimes we'll have it a little bit higher, sometimes we'll have it a little bit lower. And there's very good reason to even put it to 0 or even put it to 90, which we'll go through a little bit later on. The overlap distance is another key feature which is unique to steep and shallow. So because it's built up of numerous toolpaths, these toolpaths have to have an intersection point. They have to cross over each other by a certain distance. And the reason for that is because if they didn't cross over, we'd end up with the residual material in between the two portions. So having some overlap distance ensures that we clear up all of the material that we need to clear up. Now, I really don't want to linger on the specific details and how we get to what we do get to, but if that's what you'd like to see as we go through, feel free just to post that in the chat. So I'm going to be going through a couple of unique options in steep and shallow, and I'm going to be talking about why they're unique and why they're potentially beneficial to you. So the first one that I'm going to speak about is something that we call avoid flats. Now, if you have the machine extension, again, feel free to follow along, or make notes, even better. We have this area here called avoid flat areas. Now, when we are using 3D surfacing tools and using ball nose tools as our tool for the job, we generally don't want to machine planar regions like this, which are normal to the current work axis. So if we approach these flat areas with this ball nose tool, there's a couple of problems that we're going to have. The first one is it's extremely inefficient. So if we have this top area here, to get a respectable surface finish, we're going to have to do a very, very small step over, something like 0.02 millimeters, and it's going to take us a hell of a long time. A much more efficient way to do this is to use a flat bottom tool and machine it with that. We're going to need far less step overs. It's going to take us far less time. The second benefit is to prolong our tool life. So when we're using a bull nose tool, one thing that we really want to avoid is cutting with the bottom and the center of the tool. And the reason for this is because, well, again, there's a couple of reasons for this. Firstly, there's not much speed in the middle of the tool. The further we move out of the tool, there's more cutting speed there, essentially. Not only that, it's where the flutes meet, and there isn't really a sharp edge there generally if there's 3 or 4 flutes on the tool. So what we end up doing is more along the lines of rubbing the material opposed to cutting it. So again, avoiding the flat regions is beneficial twofold. Firstly, efficiency, an absolutely massive one. We want to cut down on the time that we are taking to machine these components. And secondly, prolonging our tool life. Solid carbide tools are expensive. We want to make sure they last as long as possible. Now, this option isn't particularly exclusive to steep and shallow, but if you are new to CAM potentially, it's nice for you to know that you can restrict your toolpath to a confined space that you've selected. So here, what we've done, I only want to machine this portion here that's confined within this chain selection. So I've used a selection method within the machining boundary, and I've simply selected these edges here. And what we get is a 2D representation of that selection that I've made, and everything that is calculated from this toolpath will be kept within that selection. So again, that's a nice way of ensuring that we're not machining anything that we don't want to, and making sure that our toolpath is as efficient as possible. There's a couple of other options which are exclusive to steep and shallow and that are very useful. So here we have an option called smooth offsets. Actually, maybe Craig can correct me in the chat if smooth offsets is exclusive to steep and shallow or not.
You are correct. It is exclusive.
Okay. So here we are again, we're in the 4th tab along. And the 4th tab again is where we define our cutting conditions, and we have an option under the shallow passes called smooth offsets. Now, to really show you what this is, we're going to have to go from this toolpath to the next one. So if we highlight both of them, what you're going to see is one of them has a fairly sharp turn to the perpendicular pass that it's going on to next. And the smooth offset has more of a filleted, smooth transition opposed to that more jerky, sudden transition. Now, the benefit to smooth offsets, again, this is potentially something which can save you a little bit of tool life. It's not going to be a game changer, but it may save you a little bit. It's going to be less harsh on the machine because it's doing less of the jerky motions. It may also save you some machining time because we're going to be staying at that programmed feed rate more often, because again, we're filleting round, we're arcing round smoothly opposed to a jerky motion, which is very abrupt. So our machine's going to like it, our tool's going to like it, our customers are probably going to like it because it's going to save us time. Now, something to notice on these passes is that when we use a step over value, the step over value is calculated from side to side here. And one thing that unfortunately happens is that as we move down this section here, that value can be violated and we don't maintain the cusp height that we want to maintain. So the way that we can efficiently ensure that we are getting a cusp height that we want and that we programmed is by using something called remove cusp set junctions. Now, again, going into the toolpath itself, going to the 4th tab where we define the cutting environment, we've got remove cusp set junctions. Now, what this option has done is put another pass diagonally here to ensure that them diagonal regions between each pass, we are removing that residual material, which isn't within the step over that we programmed. So there are a few unique reasons or a few unique features within steep and shallow that can really make a difference. And again, We're just touching on some of the 3-axis stuff at the moment. We are going to jump into some of the more complex multi-axis stuff in just a while. So again, not all of this is completely unique to steep and shallow, but there's some options in here that you may not know about and may greatly increase the efficiency of your programs. So we're going to look at touch avoid surfaces. Now, I mentioned a boundary earlier, and we selected the outer profile of this section here to keep the toolpath within that. We can use that, and we can also use something called touch avoid surfaces. We can use that exclusively, or we can use it in conjunction with a machining boundary. In this situation, I have selected this particular face here to avoid. Sometimes we do this because if it's something quite complex, if there's various different chains and it's difficult to get a boundary, sometimes it's much easier for us to just simply select the service and say, we just want to ignore that. So that's what we've done in this case. And you can see that the toolpath is exactly the same as it was up here. But all we've done now is avoid this face here. Again, that can be very useful for avoiding particular surfaces which may require a different tolerance, may require a different surface finish, or may require a different manufacturing strategy. It's something nice to keep in mind, a nice tool to have in the toolbox. The opposite of that is touch surfaces. So again, going into the second tab, and what we'll see, we've selected the same surface as in the previous toolpath, but we've simply selected touch surfaces. What that means, it's going to invert the selection as to what we had before, opposed to avoiding it. We are now choosing to just machine the surface that we've selected. And there's just one more example of something that we've selected, which could have potentially been quite difficult to get a boundary around, because remember, the boundaries are 2D. And if we're looking at a steep portion of geometry, by the time we've selected that boundary, that may end up being may end up being very small. So touch avoid can be very useful. Now, a few more options to go through here. We've got options to use parallel, and what we'll see in here is that we are using a parallel pass, so a step over of 3 millimeters, and you'll see how we are doing our shallow regions using a fixed direction of cut, and the steep regions are still acting as we would have expected them before. The benefit to using parallel is that generally when we're only cutting in one direction, we can get a superior surface finish. But one of the issues that we might get is that we may be potentially bumping up some of these faces. So on a more free-form surface like this, something like scallop will be better because it'll offset from the outer curves. But parallel and scallop can be used interchangeably, and each one suits different situations for different geometry, and they both have the benefits, both have the pros and cons. This is another parallel, but all we have different here is that we've set a fixed direction. So with parallel, what we want to do, if we select to only go down that edge, then our parallel cuts are going to run parallel to the selection we've made. But a nice tip to note is that if we don't make a past direction reference, the parallel cuts will run parallel with the x-axis. And I mentioned something called optimized perpendicular passes earlier. Now, for those who are in the mold making industry, if any of you are, this is a very powerful piece of technology which was brought over from PowerMill, which is one of the leading products in the mold and die industry. And the reason is, as I mentioned earlier, we typically like to follow one direction. That gives us a very nice surface finish. But when we're using parallel, because it's designed for shallow geometry, as we start to go up steep walls like this, where the steep wall is running parallel to our cut direction, the toolpath starts to fragment and we don't keep the constant step over anymore. So when we set the threshold angle to 90 degrees and turn on optimized perpendicular passes, when we get to a 45-degree wall, we have parallel passes which are perpendicular to the other ones. So you can see these here are all fine. These are going to give us a very beautiful result and a very beautiful surface finish on our component. But as we get to these steeper areas here, Fusion 360 is intelligent enough to input perpendicular passes to bridge the gap and ensure that them passes that are running up the steep regions aren't fragmented. And we're going to maintain that constant step over that we inputted. So moving on to a little bit more 3-axis stuff, and we are going to look at undercuts. So when we think of an undercut, what we're thinking of is a region of geometry which isn't accessible in a 3-axis orientation to our work plane. So if we look at our component here, we are coming in a very conventional manner. We've set our component up in the vise, and we are going to be coming in from the top here. Now, it's pretty apparent to see that we're not going to be able to access this area here in a 3-axis manner with a straight fluted tool. Now, a little tip, which is slightly off piece, which may be of value to people, is that we have a tool called accessibility analysis. And what that tool does, it allows us to select a component. I'm not sure where that's gone there. I think I've got one. So it allows us to turn on, or it allows us to select a component, and then it allows us to select a axis in which we're going to come from. And in green are the areas which are accessible from that orientation, and in red are the areas that are not. Now, when we select in the axis to come from, we select a planar face, a linear edge, or a true cylinder. So in this case, we've just selected the top face. And that's all saved in the browser tree over here, and we can turn it on or off at our leisure. Now, the way that we've managed to machine these undercuts in a 3-axis manner is by using a lollipop tool. Now, a lollipop tool is a tool that has a shaft, and the cutting portion of the tool is larger than the shaft, which means that we can access areas like this without leaving the 3-axis orientation. So the toolpath that we have looks something like this, and you can see this is the tool that I've used. Let me just show you how we got to this result. So I mentioned at the start that Steep and Shallow is a blend of 3D contour, 3D parallel, and 3D scallop. And we actually have the ability to turn Steep and Shallow into any of them by using the threshold angle. So when I turn the threshold angle to 0 degrees, that forces Steep and Shallow to be steep only. Now we are only using 3D contour. So we're able to get results like this from a toolpath which is designed to do steep and shallow areas. This is one of the key benefits, and I mentioned right at the start that Steep and Shallow is a very versatile tool. And this is one of the aspects which adds that versatility. Being able to tweak the threshold angle, being exposed to these more complex options as we tweak the threshold angle really allows us to do a lot with this tool. So again, let me just show, if I tweak the threshold angle, so if I turn that to 10, what you'll notice is that this option disappears. But as we turn it to 0, that option reappears. And that's because, of course, when we are machining undercuts, we only want to use the steep variation of the toolpath. So it doesn't make sense for us to expose that option when the threshold angle is anything but 0. These can be quite difficult things to find. So again, if you've got a pen and paper, or if you are in Fusion, it's worth making notes of this stuff. Threshold angle 0 means we are using the steep portion of the toolpath. When we change it to 90, we are then using the shallow portion of the toolpath. But of course, it defaults at 30. Another point that I want to talk about, and again, I apologize if this is like drinking out of the fire hose, but it's a very complex toolpath. There's a lot to speak about, and we only have an hour, unfortunately. Another aspect that I wanted to speak about is something called evenly spaced points. Now, this is applicable for 3-axis. It is more applicable for multi-axis, but what this is doing essentially is when we turn on smoothing and we select evenly spaced points, Fusion 360 will go away and it will input points that are a maximum distance of whatever we've specified there. Now, more modern machine tool controllers prefer more points. And what this generally does is it gives us a more smoother axis motion on our machine. Now, when we have a more fluent, more smoother motion on our machine, what we end up with is better surface finish results for one. And not only that, the biggest unexpected benefit we get is that we generally see a more efficient toolpath in regards to calculation time. So because the machine is maintaining the programmed feed rate more often, because of the more fluent axis movement, we generally have a more efficient cycle time and again, a better surface finish result. Now, this is useful when we're looking at 3-axis toolpath, but it really comes into its own when we start to look at multi-axis toolpath and when we have all the axes moving at once. Now, we are going to switch it up a little bit and look at some of the multi-axis, or maybe is it worth me answering a couple of questions or looking at the chat just before we transition?
I think you got everybody's mind blown. There's no questions on this. I'm just sitting back learning. So
does anybody want to actually ask a question, unmute themselves? If you do, please feel free.
Yeah, because we are transitioning from the 3-axis stuff to the 5-axis stuff now.
And if you're shy, you could just type it out in the chat and we will confer that. No.
Okay. No problem. Are any of these models available? I will come back to that at the end. I'm not too sure. I'll have to see. But Brett, I will direct you somewhere at the end, actually, something called self-paced learning, which will be very useful for you to look at. So now we're going to move into the multi-axis part of steep and shallow. And if you thought that this was a very powerful tool, looking at the 3-axis stuff, the 5-axis stuff just compounds that even more than what you already thought. So we're going to initially look at what I would probably say is the most simple area of multi-axis that we have. And this is what we know as lead and lean. So I spoke about a very prominent issue earlier within milling specifically, and this is when we're using bull nose tools and we are machining with the center of that. Let me just turn my leads and links off. When we're machining with the center of the tool, I mentioned earlier, there's no surface speed in the middle, and there's also not that many flutes there. So we are wearing the tool away quicker than we would have wanted to, and we're probably not getting the surface finish that we expected. An easy fix for this is to use something called lead and lean. So when we say lead and lean, a good way to think of it is when we are leading with the cutting direction. So if I just show you that on here, that'll be better than me butchering the explanation. If I can find a point. So what you'll see there is that our tool has been knocked over slightly. Now, this is always going to be leading forward and leading parallel to the cut direction. So if I give this a play, what you'll see is that we are constantly tilted forward there. If it was going 2 ways, the tool would then come back the other way. But this is a very good way to move that cutting point from the center of the tool and to get it more onto the flutes. You are going to see a better surface finish result using this technique opposed to using the middle of the tool. Now, we can also do something called lag. And when we think of lead and lean, again, a good way to think of it is lean is leaning forward, lag is lagging behind. Lead is generally preferred, but I'm sure that lag has its applications within the industry. And then we also have something called lean as well. I'm sure most of you have probably figured out what lean means, and lean is essentially perpendicular to lead. So opposed to leaning parallel with the cut direction, we are now leaning perpendicular to the cut direction. Again, similar reasons why we do this. One reason could be to potentially avoid any work holding that we've got. So that would be a very valid use case in this example. But again, primarily one of the key values here and one of the key benefits is getting that cutting point from the center of the tool. Just check my time, 30 minutes past. Okay, so I've got about another 10 minutes. I just want to ensure that we went through how we set that within the toolpath. So if none of you have used any multi-axis tools within Fusion before, you'd be used to the 5 tabs on the top here. When we have multi-axis capability, we have this 6th tab here, which is our multi-axis tab. Now, it's going to be very difficult for us to get through everything in a comprehensive manner today, but what we've done here to get lead and lag is select lead and lean as our primary mode. And we've simply just been able to input an angular value within one of these areas. It is genuinely that easy to create a multi-axis toolpath, and that's one of the key benefits to using Fusion as your multi-axis solution. It's the power, it's the versatility, it's the ease of use, it's the familiar user interface. There's a lot of benefits. So if we move on to another example here, and this is a vastly different part to the last example, showing you how many different kinds of geometry steep and shallow can handle. And this is what we know, or what Craig would call a very complex feature-rich part with various vertical walls, various pockets, cavities, and it's extremely difficult for us to machine a component like that. One being it's got super steep pockets. There's a lot of different angles, a lot of different free-flowing surfaces, a lot of steep areas, a lot of shallow areas. And one of the biggest problems that we end up having is that when we come to an area like this down here, I believe this is a 3-axis toolpath if I simulate it, what you are going to notice is that I cannot machine this vertical face with an appropriate length tool in a 3-axis orientation. For me to be able to machine this, I would need an outrageously long tool, or I would need to do a series of 3+2 indexable moves, which is just not a very efficient way to do it. So one of the lowest touch forms of multi-axis that we have within steep and shallow is something called automatic collision avoidance. Now, before I show you the magic behind the simulation, the way that we do this is by setting a primary mode. This is eventually going to load. We set up a primary mode, which is vertical, and the collision avoidance is set to automatic. That's all I've done. There isn't any more magic. It's not smoke and mirrors. That is literally all that I've done. And now what Fusion 360 does here is that it calculates a 3-axis toolpath, and then it inputs appropriate tilts away from the component where it knows there's going to be a collision with a shaft tool holder. So if we go down here, before our tool holder was colliding with the component, what you see now is that Fusion 360 has automatically tilted away from the component by an appropriate amount to avoid the collision. Now, the benefit here is that we are able to use a tool which is a sensible length, and we have managed to machine the entire component, or should I say the 3D surface component, in one go. Another point to mention is that we generally don't want to do multi-axis where we don't need it. When we have excessive C-axis motion, we tend to suffer from a surface finish standpoint. So one of the key benefits to automatic collision avoidance is that if it knows that there isn't any danger of a collision, it's going to stay in a 3-axis mode. But when we come to areas like this, where it knows there is a collision, it's intelligent enough to, and it goes back to 3-axis, it's intelligent enough to tilt away from the component by an appropriate amount. So it really is super clever, very automatic, very useful if you are thinking of machining any complex parts in the future. Technology like this makes you much more competitive in the market. You imagine trying quoting for a job like this, only having 3-axis capabilities. You are absolutely not going to compete with others who have multi-axis machines and who have powerful multi-axis technology. Now, I am definitely not going to have enough time to get through all of this stuff, but I am going to run you through a couple of more examples. So here we have a what I would describe as a fairly simple component, but if we scratch beneath the surface just a touch, what we're gonna quickly realize is that if we want to be able to machine this component with a sensible size tool, we are not going to be able to do it in a 3-axis manner. These red areas at the bottom here is Fusion telling me that you really need to take a look at this toolpath, because your holder is plowing through the component, and that's not going to be good for anyone. So as I said, one option, it's not a viable option, but one option is to have an outrageously long tool. And one of the problems that we have here is the surface finish on this component is going to be not desirable at all. Our tool is actually going to deflect, meaning that we're going to leave excess stock on the component, and we're probably going to break our tool if the material's got anything about it. So what I have done within Fusion is I have used our multi-axis options, and I've used something called 2-point. Now, when we use 2-point, what we do, we create a point within the design workspace. And when we're using 2-point or 2-curve, that point or curve is generally lower than our workpiece, and it's generally suited to protruding forms. And what you'll notice is that as we simulate this, if we imagine that the middle of our tool has an infinite axis going through it, that infinite axis is always going to maintain contact with that point. So we end up with a toolpath that looks like this. And this is a vastly more efficient toolpath than the one we had before with the super long tool. Now I'm going to go through one more example because we are just coming to time, and this is slightly different. So I just spoke about 2-point, and now we're going to look at something called from curve. Now I just mentioned that when we using multi-axis methods such as 2-point or curve, it's generally suited to protruding forms. And you've probably guessed that when we're doing from, curve, or point, this is more suited to recess forms such as this. Now, again, let's tee it up with the problem that we've got. It looks like a fairly simple component, but upon simulation, we have got a whole load of areas where our tool holder is colliding. Now, we all know the alternative, use a longer tool. I really don't want to do that. So what I'm going to do is use from curve. And you'll notice that this curve here, my tool is always maintaining contact with that curve. Now I'm going to throw one last thing in the ring before I hand over to Craig. I don't like this toolpath, and the reason I don't like it is because the axis tilt is far more than I want it to have. So there's a really nice option within the multi-axis tab that allows us to restrict the degrees that tool tilts to. So we have primary mode from curve, and in our override tilt angle, we have a preferred angle of 28 degrees. Now, what this means is that our tool is still being driven by the curve, but it's now being governed by the preferred tilt angle to ensure it doesn't go further than what we have specified. Now, that was a hell of a lot of stuff within half an hour. I'm sure it may have been quite difficult to keep up with it, but again, hopefully that really demonstrates the power of steep and shallow. It's one toolpath, and it's kind of crazy to think that all of that stuff is in one toolpath, but it really is the case. So I guess we'll check the chat. Doesn't seem to be anything in here. I'll now hand over to Craig, and I'll post a few links to the chat at the end to some of the self-paced learning stuff. But Craig is going to walk everyone through what the next stages are for this toolpath. Over to you, Craig.
Okay, thank you, Dylan. So we continue to enhance steep and shallow. I'm going to just explain some of the areas that we are working on or will soon start working on. So kind of top left, steep and shallow open pocket strategy for shallow. So one of the examples Dylan showed at the beginning, actually, where he was using scallop and especially where he was smoothing the scallops, was that there's quite a lot of changes in direction in the toolpath, and wherever you get a sharp change in direction, even if you smooth them, it's gonna reduce the quality of the surface finish. So a way to avoid that is for the software to totally recognize where the tool can approach from the outside. And if we take a look at that shallow region, which is displayed in the top left of this screen, then the tool is free to approach from the outside on the inside of that shallow region. So as an option, that can be switched on, and then that's what will happen. It results in far fewer changes in direction in the toolpath and therefore a superior surface finish. Okay, if I go bottom left, what Dylan also showed was some kind of tricks which are not very discoverable. You now know how to do it because Dylan just showed you, but you probably find it hard to discover it by yourself. Dylan was kind of tricking the system to give us just steep only or shallow only by changing the threshold angle to 0 or 90. So we've made that much more obvious for a user. This is a relatively simple enhancement, but now there's an option in the dialog to say machine regions, I want steep and shallow, or shallow only, or steep only. And we'll get all of the additional options that come with a shallow only, such as the optimized parallel, those kind of things which Dylan showed, and the special options which come with steep only, such as the ability to machine undercut. Upcoming, we're introducing a new strategy for steep regions. Today it uses 3D contour, and 3D contour is a good strategy for steep. Where it doesn't do the greatest job is when the floor of the pocket is not flat. And I don't think this is the greatest image, and I blame myself for that. But the floor of this pocket is not flat, it's inclined. And what you typically get with a 3D contour toolpath is entry and exit leads entering in that bottom corner, which is going to give quite a poor surface finish in the bottom corner. So this option is going to actually take the 3D curve from the base of each and every pocket in the part, and it will have a constant step over based from that base curve. So what that essentially does is eliminate any entry exit marks at the bottom of the steep wall. Again, the whole purpose is to give you a superior surface finish. And another enhancement, which is not just for steep and shallow, it's across the board in Fusion, is, and these are two related things. In Fusion, you can define your fixtures on the setup. By default, unless you're using touch avoid, then the toolpath will simply pass through the fixtures. So we're going to change all of the strategies, 3D strategies in Fusion, so that if you've defined fixtures, it will by default always avoid them with a user specified clearance. Also with touch and avoid, at the moment, you've got the option to touch or avoid. You can't touch and avoid. So we're going to really add flexibility to touch and avoid by allowing the user to specify multiple touch groups and multiple avoid groups. Each group can have an independent stock to leave in the case of touch, or an independent clearance value in the case of avoid. So this really enables you to, if you're machining in a shallow region, you don't want the tool to bump into a near steep wall because it will mark that wall. So you can specify these groups and just really enable automation by pre-specifying where you want clearances or additional stock to leave. Okay, do you want to move on one, Dylan? Okay, so Dylan showed you one example at least with the 5-axis automatic collision avoidance. And of course, the priority for that feature is to avoid collisions. And it does that very, very successfully. But what we sometimes get is, and again, Dylan related to this to a degree when he was talking about the contact point on the tool and how, it's undesirable to contact on the tip of the tool. But what is also undesirable is the contact point on the tool. If that's constantly changing between passes, we'll get differing amounts of deflection, and even issues such as the tool deflection, the runoff on the tool, how well the tool cuts at that point. It's going to be changing if you change the contact point on the tool. So the automatic 5-axis collision avoidance, we're putting huge effort into keeping the contact point on the tool consistent, much more consistent. And again, that's all, the real benefit that we want is better surface quality at the end, on your finished part. And that's the same kind of deal for the image on the right, where we're looking to have much smoother C-axis transitions as well. There's a small video playing. But wherever we get axis reversals or jerky motion on a C-axis, we're going to see the mark visually on the part. So we're doing huge amounts of work to really make that rotary axis motion as smooth as possible, whilst obviously still avoiding any collision. And Dylan is actually part of the team who is testing out all of this code for us right now in the tech center in Birmingham, UK, where we've got quite a wide range of 3- and 5-axis milling machines. So as we develop it, Dylan and his team are testing out the code for us to ensure that what we're doing works well. Some of the other things we're doing, you saw Dylan exclude flat regions. Now that was flat regions which are parallel to the XY plane, essentially. But we're about to introduce a new strategy to automatically machine all flat regions, including inclined flats, if you've got a 5-axis machine tool. So we're going to add the option into Steep and Shallow to exclude inclined flats if you're machining them on a 5-axis machine tool. We're also going to enable you to define a cusp height opposed to a step over or a step down, should I say. Because dependent upon the gradient of the surface, the step down should vary if you want a consistent cusp height remaining. So that's going to be added. So the user, it will be simple. You will specify a maximum cusp height, and Steep and Shallow will do the hard work and provide you with a toolpath whereby the step down actually varies to provide you with a more constant cusp height. What else are we doing? We've already spoken about the steep regions. Dylan showed you undercuts with the lollipop tool, and a problem that we can get into is defining good entry and exit points where the toolpath actually stops below an undercut, because it needs, sometimes you need like a large arc to ensure that you clear the tool outside, from below the undercut to retract out. And that can be quite a guessing game, and it can be painful. You try one value and it doesn't quite work, so you try another value and you have to keep recomputing all of the time. So we've already got this in preview, where we've got much smarter leads and links which automatically detect if the tool is under an undercut, and if so, the leads and links will be automatically adjusted. Perhaps the radius, perhaps the span angle of the arc, all of those things can be fully automatically adjusted to clear the part from under the undercut safely. So that's generally what we've got going on for Steep and Shallow. Happy to take any questions on what's there or what's coming.
Thank you very much, Craig. And that is the end of what me and Craig had.
Is there any questions? I've typed in some chats and the text disappears. So I'm wondering if my Zoom is acting funky. Yeah, is anybody else seeing any comments? Does anybody have any problems with
I can see what you posted, I think.
Okay, good.
Yeah.
You said feel free to ask your questions here in the chat.
Yeah. Okay. So you're seeing my stuff. I'm just not. That is bizarre.
Yeah.
I've never had that happen before. So I guess there's no questions. I mean, it seems like a pretty deep topic, and it's awesome. It's helpful. So I want to thank you guys. If there's no questions, we'll just wrap this up. And I go to the next slide, please. So I'm going to post some links into the chat. Dylan, you had some links as well, right?
Yeah, I'll grab them once I've stopped sharing.
Excellent. So you can be a community conversation speaker if you'd like. If you have expertise in a certain topic, you can propose those, just email me. So we're always looking for more speakers. Next, please. Excellent. I gave you a bunch of links so that you can follow along and use those. I'll also post those to the event page along with the recording by tomorrow. So you can explore the many different ways to connect to the Autodesk community, including user groups, global network. There's the forums, there's all different types of ways, LinkedIn. I also put in our community journal, which is the community team's blog, and then the community voices. Community voices are customers blogging articles on industry and products. And I would love to get some milling and some Fusion 360 bloggers in there. We have Inventor, Revit, Dynamo, AutoCAD, AutoCAD Electrical, a lot of different products. Maya, we would love to get some. So if you're interested in becoming an author on that, please feel free to reach out. We do have a link for that, or you can email me direct at shaan@autodesk.com. So thank you for attending today. There will be a little simple survey at the end that helps us understand what you liked and how to, what kind of content you'd like to see in the future. So when you leave, please take the time to complete the survey. And thank you very much, Dylan and Craig. I appreciate it.
I'll stick the link that I had in the chat. So this
Awesome.
link is in reference to what I believe David asked. So we have something called the Self-Paced Learning Portal, and what this is pretty much what the name describes. It's a series of videos which are designated to specific areas. So we have one for the product design extension, we have one for milling in general, we have one for design in general, but we also have one for the machine extension, and it's around 26 videos, and you can essentially follow on in your own time and follow on as you want. And I believe a lot of these models are also in the CAM samples as well. So take that link, save it to your favorites, and whenever you go back and you can't remember how something was done, all of the information should be in one of those videos somewhere.
Excellent. Thank you, Dylan. And I should get a list of all the chats, and I'll get your link there. If I didn't, I'll reach out to you, and we'll put that on the event page as well as throw it out in social. So thank you, gentlemen. Appreciate you staying up. What time is it there? It's got to be late afternoon.
5 to 7.
Oh yeah, it's beer time. So I'm sorry. I appreciate you guys jumping in on this. So
no problem. My pleasure.
You go on about your evening. Thank you. It's a pleasure to meet you, and it was fascinating to see a lot of that. I haven't done machining in a long time, but that's awesome to see the way Fusion does it. So thank you.
Thank you, everyone. Thanks
Cheers,
for joining.
guys.
Cheers.
Bye-bye.
Bye.
Bye-bye. Bye-bye.